If you're searching for an engineering role in 2026, you're in luck because we're about to enter the biggest opportunity window since the tech boom of the 2000s, and it's happening right here in Australia's energy sector. 82% renewables by 2030, net zero by 2050, and over $140 billion of investment to get there. But is it the next hype story that'll die out in 5 years, or is it the best career bet you can make in 2026? I'll answer that with the 3 insider insights you'll need if you're serious about getting ahead of the crowd, the exact information I used to break into energy and reach the senior level in just 3 years. But before I tell you why energy is different from every other engineering sector, you need to understand the scale of what's happening in Australia right now, because the numbers are shocking. Australia is forecast to invest over $140 billion into its electricity system between now and 2050. But here's what most entry-level engineers miss about that figure. They assume the $140 billion is funneled straight into asset growth to handle the increasing demand for electricity. A couple wind and solar farms and a few batteries on top of the existing fleet. Instead, it's a rebuild focused on replacing the centralized supply that has powered Australia for the last 60 years. Because the fact is that over 90% of Australia's coal fleet will retire by 2035. And with the ambition to replace each one of those centralized plants with a decentralized electricity source, the ultimate result isn't just a network upgrade, it's an entirely new system. And a rebuild of that magnitude doesn't come without engineers. Tens and thousands of them. Which means that if you position yourself right, you're not competing for scraps. Companies are competing for you. But a number on its own is easy to dismiss. Where that money goes matters much more than how big that number is. And when you dive deeper into where it's going, you hit something that most people have never heard of. To enable a fully decentralized electricity system to operate successfully, you must be able to physically move electricity from the location where it's generated to the capital cities or load centers where people live. In the energy sector, that means new transmission lines, and a whole lot of them. The 2024 Integrated System Plan calls for over 10,000 kilometers of new high voltage transmission lines, which for context is enough steel to run a line from Perth to Sydney and back again. It's truly the largest engineering program in Australian history, bigger than the Snowy Hydro scheme and much bigger than the NBN. There's several projects underway right now that show this scale in action, such as HumeLink, VNI West, and Marinus Link. Each one of these is a multi-billion-dollar build that relies on engineers to support design through to commissioning, and every single one is running behind schedule because there aren't enough engineers to build them and enough money to push them along. But here's the comparison that made this click for me. In the 2010s, if you were a young software engineer, the smart play was San Francisco. Silicon Valley, that's where the capital and the talent were flocking. From my perspective, Australian energy right now fits that exact mold. The capital is here, the projects are following, and the industry is screaming out for talent. And the best thing is, if you're in Australia, you don't even have to leave the country. So whilst the scale is undeniable, that alone doesn't get us engineers excited, because what every engineer truly craves is the knowledge that only technical complexity can satisfy. You see, back in the 1950s, the Australian electricity system was designed with a single job in mind. Take a small number of very big, very predictable coal generators and deliver their output to consumers. Big spinning synchronous machines at 50 Hz feeding passive consumers with typical load profiles. How this system is being run in modern day is in a way that designers never imagined. Because last year, South Australia ran on more than 80% net renewables, whilst the entire national electricity market regularly sits above 70% on sunny, windy days. So we're taking a 70-year-old system, pulling out the machines it was designed around, and plugging in something completely different, all whilst ensuring the lights stay on 24/7 for 25 million people. That's not a problem that can ever be solved by a single project, but an open engineering problem that is grand enough for thousands of engineers to dedicate their whole working careers to. To get a sense of the technical complexity at hand, I want to take some time to highlight 2 technical challenges the industry is currently rallying towards solutions for. The first challenge that I'd like to highlight is system inertia. Synchronous generators are huge spinning masses that give the grid a buffer when something goes wrong, effectively defining how a power system responds to a fault, where the inertia constant is defined as the total inertia connected to the power system in a relative sense. And all of that is multiplied by the nominal frequency, which in this case is 50 Hz. Using this formula as an example, you can quickly see that as the inertia constant gets smaller, the rate of change of frequency naturally increases for the same size fault. What this looks like in reality is that as these synchronous generators, i.e. the coal fleet, disconnect from the network or retire, our inertia constant naturally gets smaller, meaning that we're seeking to increase this inertia constant in order to maintain system security or the ability for the power system to respond to faults by procuring that inertia from other sources. This is where things like syncons with flywheels or grid-forming inverters are being investigated to provide that inertia source in a renewable network. That naturally leads into the second challenge that I'd like to highlight, being frequency control. Now, in order to maintain nominal frequency being 50 Hz, the grid has to sit between the top frequency bands of 49.85 Hz and 50.15 Hz. In the power system of the 1950s, where a lot of these synchronous generators relied on to maintain frequency, a mechanism called a governor was used. A governor is effectively a way for synchronous generators to spin up in RPM, or revolutions per minute, over time. So in the event we had an under frequency event where we were down toward this lower band of frequency, that governor could simply raise the RPM of the spinning mass in order to increase the frequency of the power system. And similarly, if we were in a higher frequency band, that governor could reduce the revolutions and reduce down to the lower band. However, around a decade ago, as these synchronous machines, number one, were getting priced out of the market, but number two, were also beginning to retire, the need for this frequency control ancillary services became quite critical. And that is what led to what is now a critical reliance on battery energy storage systems to provide that FCAS service, being the emergency raise and emergency lower in the energy market, which effectively emulates the traditional performance of a synchronous generator. Where in the case we need to increase frequency, BESS can inject reactive power to increase frequency from a lower band to a higher band, and similarly go the other way, because at its core, frequency is purely a seesaw of supply and demand, where if supply outweighs demand and we have a over-frequency event where the seesaw flips up on this side, either supply must decrease or demand needs to increase, i.e. a battery charging, in order to maintain nominal frequency, and vice versa, where demand outweighs supply and we either then need to load shed or increase supply. So as this example illustrates, in a system that requires instantaneous power that may not be able to be procured from variable renewable energy sources, BESS become critical to be able to balance that supply-demand curve and ultimately maintain frequency. In summary, don't worry if some of this sounds complex. That's exactly why we need engineers like you to solve it, because every one of these problems represents career paths that didn't exist 5 years ago. And central to that are engineers who can think outside the box and question the norm, because that's ultimately what the industry is relying on for the next 30 years in order to achieve the targets that have been set. So the scale is there and the technical challenge is inconceivable. So the only question left to answer is this a safe bet? Or will you just spend 5 years building a career in something that gets pulled out from under you? Australian energy policy has something almost nothing in the country has. Fundamentally, both major parties agree that the grid has to be rebuilt, but they fundamentally disagree on what the energy future looks like, whether it be doubling down on baseload power from nuclear or the more dynamic renewables and gas combination. Regardless, they don't disagree that the existing coal fleet is reaching end of life and is becoming unreliable, and therefore must be replaced with something new. What that means for your career is that the engineering workload won't go anywhere based on who wins the next election. Engineering roles will exist in every version of the future, which is exactly why grad programs in energy are expanding whilst tech companies are stuck in a hiring freeze. But you may be thinking, haven't we seen this all before with tech? What is going to happen 10, 20 years down the line when everything flushes out? But don't worry, there's a second argument that matters more, and it's got nothing to do with politics. Since the internet boom of the 2000s, the natural move for every ambitious engineer is big tech. Software pays pretty well, but with the introduction of AI, the world has witnessed entire engineering teams at FANG companies like Google and Meta and Amazon get laid off in a single week. Fortunately for you, the critical infrastructure that underpins the energy sector pretty well ensures it won't play out like that. Because the role that energy plays in society will never diminish. It won't get disrupted overnight by new AI model release, and it won't get offshored because the work is done on Australian soil under Australian regulation. Because no matter how good AI gets, I can assure you that the companies won't replace commissioning engineers who make the call on whether to energize new transmission lines with an AI model. No matter how you spin it, energy simply isn't a hype cycle because it's underwritten by a generational infrastructure rebuild that will span well beyond your entire working career. So if you're an ambitious engineer, there's simply no better career bet in 2026. But here's the thing, the best entry-level roles get snapped up first, and all of the 2020 intakes are about to close. So before you rush into a decision at the last minute that will end up costing you a decade to fix, take the 2-minute quiz at the top of the description to get your personalized roadmap to Australian energy before it's too late.